All right, class, today's lesson is the alternating series test. To use the alternating series test, your terms have to be alternating from positive to negative or negative to positive. Okay, they must be tending towards zero, and the terms must be decreasing. Decreasing means all your terms have to be positive and they tend towards zero. Determine each of the series converges or diverges. Well, our negative 1 to the n plus 1, if you put a 1 in, then a 2 in, and a 3 in, that becomes negative 1 and then a positive 1. I'm sorry, it goes positive 1 to a negative 1 to a positive 1. So my terms are going to alternate. So my first term is going to be a 1, and then we're going to get a half, and then we're going to add a third, and then we're going to subtract and get a fourth, and add a fifth, and so on. So this series does converge based on the alternating series test because my terms are alternating and they are decreasing towards zero.
Hey, Mr. Klein, please let me do the next example.
Okay, Alex, you can do the next example. Our next example will be based on negative 1 to the n plus 1 over 2n over 4n minus 3.
Hey, Mr. Klein, please let me do the next example.
Okay, Alex, let's look at negative 1 raised to the n plus 1. Negative 1 raised to the n plus 1. What happens to those terms? Yep, those terms do alternate. Okay, and the terms are getting smaller because doubling something compared to quadrupling something, the numerator is going to be much smaller, and my limit as n goes towards infinity ends up being 1/2. So although my terms do alternate because my negative 1 raised to the n plus 1, my term values are not approaching zero. So by the nth term test for divergence, this series diverges. In my next example, it says we have n over n plus 2. Well, the first thing we do is check to see if my terms are going to zero. Since my terms limit as n goes to infinity ends up being equal to 1, then this series diverges. Now this next one's a little tricky. We do have 1 over n, and then we have this cosine of pi, or n times pi. So cosine of n times pi is a fancy way of getting this series to alternate. When you put a 1 in, then a 2 in, and a 3 in, you get cosine of pi, then cosine of 2 pi, and then you get cosine of 3 pi, and so on. So cosine pi is negative 1, cosine 2 pi is positive 1, cosine 3 pi is negative 1. So these terms alternate between negative 1 and positive 1. So I get negative 1 over 1, which is negative 1, and then I have positive 1 over 2, and then minus 1 over 3, and so on. So these terms do alternate, and they are decreasing towards zero. Therefore, this series converges. Now, with an alternating series, you can actually bound the error by estimation a lot easier than Lagrange error bound. For example, the sine curve can be approximated with the odd polynomial x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And by putting a 1 in, I get 1 minus 1 over 6 plus 1 over 120. This summation here is my estimation. Now, what this theorem says is is that the partial sum is within R sub n, the remainder of the actual sum is less than or equal to the first neglected term. Sounds all complicated, but all it is what was the first term that I omitted on this problem? That was x to the 7th over 7 factorial. So by putting a 1 into that, we know that my estimate is no more than 1 over 7 factorial off of the exact answer. Again, that's the first omitted term. Here we have an example. It says find the series error. So we're going to bound the error. We're saying our error is going to be no more than our bound. And my bound is going to be my first omitted term. Okay, so we're estimating something using the first 100 terms. Well, that means, since we are starting at 1, that means we are going to bound my error by simply using the number 101. So we're going to have negative 1 raised to the 101 plus 1, which is 102, and then times 1 over 101. So this is a positive 1, so my error will be no more than 1 over 101. This problem says estimate the amount of error involved in the approximation of f of negative 1 for the first 3 terms. So since we're starting at 1, they will line up. So I'm going to put a negative 1 in for my x. So my problem reads negative 1 to the n times n to the n over 3 to the n times n factorial. We're going to be looking at the absolute value of the error. We don't care if the error is positive or negative. So I'm just going to throw that alternation part out. And since we're using the first 3 terms, we know we're stopping after n is 3. So my error will be no more than putting a 4 in. So my error is less than 4 to the 4th over 3 to the 4th over 4 factorial. Our last problem here says determine the number of terms required to approximate the sum. Well, we got to be careful here because this says n equals 0. So if I said this was n equals 1, okay, that would mean I'd have to make this n minus 1 up here, and then this being n minus 1 factorial down here. So let's look at it that way. So I have summation of negative 1 raised to the n minus 1 over 2 to the n minus 1 times n minus 1 factorial. I like to always start my series at 1 when we're talking about this, the remainder theorem. So when I put my 1 in, my 2 in, my 3 in, it says approximate how many terms are needed. So no matter what we do on top, it's always going to be a 1. So we're looking for the denominator 2 to the n minus 1 times n minus 1 factorial. We need that to be less than 1 over 1,000. Okay, and we can see this happens when we're saying if we stop it and look at the next term, we're putting in n plus 1 in for the n's. So I'm going to get 1 over 2 to the n plus 1 minus 1, or 2 to the n, and then this is n factorial. And the value, as long as you put a number in that's greater than 4, we end up being less than 1,000. So we have to have at least 5 terms.